All right, so we have 4 combined circuits to look at. But let's begin with this one. Here, the 3 components are connected in series. The resistor, the inductor, and the capacitor in series. Now, in series means that they are connected end to end. Or you say there is only one path for current to flow through. Is that okay? Now, the first point I'd like you to take note of is that if I close this switch, all right, and then I pause this, notice the value of the current on this ammeter. Can you see it's the same thing? So the first point is that whenever these 3 components are connected in series, the same current flows through the 3 of them. Is that okay? So the same current will flow through this guy, through this, and through this. Is that okay? All right. The second point is that potential drop across each of them will be different. So let me show you. If I connect this voltmeter to, across the resistor, you see the value. Then I connect this guy across the inductor. Notice the value. Sometimes this may not be accurate. So, okay, you see, we are getting different values. All right, but the point is that can you see the voltage drop across the resistor and the voltage drop across the inductor? They are different. Is that okay? Of course, if I connect this to this other one, the voltage drop will also be different. But I need you to know that the current through the 3 of them must be the same. All right. Now, I need you to know that we have already covered this. This, we are here right now. Is what we are considering. And we've also covered this. Now, what's the difference between reactance and impedance? Let me show you this. Okay, actually there are 3 of them: resistance, reactance, and impedance. And of course, the unit of the 3 of them is the same ohms. All right, so let's toggle with these circuits that we have here. What about this one? We have resistance here. Can you see only the resistor is connected? What about this one? We have reactance, but then it's going to be capacitive reactance. So you put sub C, all right? This one, reactance, inductive reactance. This one, reactance. Later I'll be telling you how that the formula is XL minus XC, all right? So, but reactance. Now, as long as there is no resistor, it's reactance. Now, what about this one? Can you see a combination of a resistor and a capacitor? This is impedance now. Okay, the overall opposition to the flow of current is impedance. And the formula will be this: square root of R squared plus XC squared. It's very simple. What about this one? Impedance. Okay, we have a resistor and an inductor. So R squared plus XL squared, like that. What about here? Impedance. Okay, the same thing. So R squared plus XL minus XC squared. Is that okay? Okay, so what did we notice? We noticed that if a circuit contains only the resistor, this is resistance, and the unit is the ohms. If a circuit contains only an inductor or a capacitor, it's only a capacitor or a combination of the 2 of them, LC, then it is reactance, and the unit is also what? Ohms. Okay, Z, if a circuit contains RL or RC or RLC, then you're already talking about this guy, impedance. Is that okay? So take note of these definitions here, and then the unit of reactance and impedance, we've established that it is the ohms. All right, as long as it has to do with the opposition to the flow of current, it is ohms. Okay, now we are dealing with 4 circuits, 4 combined circuits. So I'm going to start with RLC, okay, then RL, RC, and LC. These are the 4 combined circuits that we want to consider in this video. Okay, so these are the 4 circuits that you're likely to see. So this one is LC. Okay, this is LC, this is RC, this is R and L, and then this is RLC. Okay, so let's start with RLC. Okay, the overall voltage is VZ. We said impedance, right? Z represents impedance. So now we said the same current will flow through the 3 of them, all right, but different potential drops. So this is VR, potential drop across R. This one is VL, and this one is VC. Okay, so the overall voltage, okay, I think I should establish these ones first. So VR, you remember, is current times R. VC is current times XC. All right. VL is current times XL. That's inductive reactance. And then VZ will be what? Current times the overall impedance. That's impedance. Okay. All right. So for this one, if we have, let's start with this circuit. Now I'm going to list out the formulas, then we solve just the problem, and then I'll show you how to derive them. All right. So here, start with V. VZ is equal to, for this circuit, the square root of VR squared plus VL minus VC squared. Okay, and then the Z, since we have impedance, will be square root of R squared plus XL minus XC squared. Okay, now remember that Ohm's law still applies here, just like we said. VZ is equal to current times the overall opposition to the flow of current. Okay, so just note these 3 formulas with respect to this first circuit, this one. So when we come to here, we just modify what we already have. So this one will also be VZ, all right, since we are dealing with impedance. So VZ equal to the square root of VR squared plus VL squared. Can you see? Since we don't have C, so it will just be VR and VL. Is that okay? And then the impedance will be R squared plus XL squared. It's as simple as that. And then, of course, from the overall voltage from Ohm's law, VZ, just like we saw before, I times the impedance. Okay? All right. What if we come to here? This other circuit, RC, the same thing, VZ will be equal to square root of, excuse me, VR squared plus VC squared. Can you see? So we've reduced this one to this. And then Z now, impedance will be equal to the square root of R squared plus XC squared. Did you get that? Okay, and just like we have already seen, Ohm's law, VZ is also current times what? Impedance. Okay. Now what about this guy? Okay, so we have only L and C, and this is reactance. All right. Now instead of, it's my biro. Okay, so we want to modify this. Instead of this, it will now be X. It will now be VX. It won't be VZ. VX, okay, will be equal to square root of, now we don't have R, so it will just be VL minus VC squared. And you remember that this square root will cancel this squared here, so that you'll be left with Vx is equal to VL minus VC. All right. Then when it comes to the impedance, instead of this guy, okay, we make it X. X will be equal to the square root of XL now, XL minus XC squared. And the square root sign will cancel this square, all right? And then you have X is equal to XL minus XC. Don't worry, I'm going to derive this if we have time. Okay, so take note of this. All right, so let's look at this question together. Now, look at the circuit here. The question says in the series AC circuit shown below, the potential difference across the inductor is 8 volts, and that across the resistor is 6 volts. The source voltage is what? That's the overall voltage. So they're asking us to find the source voltage. This one, and that is VZ. You remember? So you just put down our formula. Let me change this. Okay, you remember our formulas? The three of them. VZ, remember it's Z because we are dealing with R and L, so impedance is involved. So VZ is equal to VR squared plus, in this case, VL squared, only VL, right? And then you remember the impedance is equal to what? Square root of R squared plus XL squared. So once you put down this, and then the third one, VZ is equal to current times the impedance. So once you take note of these three formulas, you are good to go. So which one do you think will be fitting for this question? Is this one. All right. So you just plug in the values. VZ is equal to, now we are given that the VR, I modeled this up. So this one is VR, sorry. Why this one is VL, okay? So we've changed it. All right, so 8 squared plus 6 squared. And that will give us 64 plus 36, which will be what? 100. Of course, we have 10 volts. So the correct option is B. All right? Okay, let me quickly show you how we derived these equations. Let me use the overall one. Now, I hope this will not consume much time. Okay, so how did we derive this? VZ is equal to the square root of VR squared plus VL minus VC squared, or it says Z is equal to the square root of R squared plus XL minus XC squared. So how do you derive this? Now you remember when we handled pure resistive circuit, pure inductive and pure capacitive circuits, all right? We saw the concept of phasor, and we said a phasor is just a rotating vector used to describe any of the AC quantities, whether current or voltage. Okay, so if we establish the three vectors we have using VR as the reference one, so it will be pointing in the positive x-axis direction, all right? That's along the positive x-axis. So VR, since it is in phase with the current, all right? Remember this. Okay, and then VL will be leading current. So we'll draw it like this, and then VC should be smaller, but it will be lagging current. Okay, so we have three vectors here to parallel with. How do we resolve the three of them? How do we find the resultant vector? You start with these two, the one along the vertical, VL and VC. So since they are, the angle between them is 180 degrees, or you say if two vectors are in the opposite direction, you just subtract. Okay, so that means we are going to have a resultant which will point in the direction of the bigger one. So this will be VL minus VC. Okay, and then we still have our VR. Okay, so now the two of them are inclined at 90 degrees. Okay, how do you find the resultant of two vectors that are inclined at 90 degrees? You remember your parallelogram law of vector addition. So from the point of intersection, the diagonal becomes our resultant, and we are going to call it VZ. Okay, now we can bring this one over to this other side. Don't mind the poor diagram I'm drawing here. Okay, so here is still VL minus VC. Is that okay? And the angle here is phi, the phase angle. Okay, so from here now, how do we find the hypotenuse, which is the source voltage, or VZ? You use Pythagoras theorem, right? So I'm going to come down here. VZ squared is equal to VR squared. Remember Pythagoras theorem? Plus, this time around, we have VL minus VC squared, like this. Okay? And if you break this apart, VZ is IZ squared is equal to IR squared plus IXL minus IXC squared. Okay, now if you factor out I squared, okay, in the right hand side of this equation, then you notice that this I squared here will cancel the I squared that would have been factored out here. All right, so that you will now be left with this. Okay, let me see if I can explain further. That's if my time is